Okay, today we are going to talk about metamorphic transformations. Now, when we look at rocks, and especially metamorphic rocks, and let us look at one of the metamorphic rock. This is a metamorphic rock. It has a planar surface here, which is full of mica. And if you look at a cross section here, we see layers which are white, which are non-mica layers, and the layers which are darker, which are mica layers. So these are known as quartz and mica domains. But when we look at another rock from which this might have transformed, and I can smell this rock, and it gives an earthy smell, and it is known as shale. This is the rock which has transformed into this shiny rock. We need to have an idea about how this transformation occurred. But prior to that, we must understand that bulk of the transformation from this rock to this rock involved no chemical change. That is, the overall bulk chemistry of this rock and this rock, other than the volatiles or water, is same. And this is known as isochemical change. Now, how do we understand or study this transformation where the bulk chemistry does not changes from one entity to the other? We can consider the metamorphic rock as a system, and as you know, system is any part of universe in which we are interested at a particular moment of time. A system is defined or is constituted by phases. Phases are physically and chemically homogeneous part of system and they are mechanically separable. When we look at phases in terms of the chemistry, then the system has a chemical composition which is defined by components. Now, components are minimum number of chemical species which can define all the phases. The emphasis is on minimum number of chemical entities or species. Now, we will try to find a relationship amongst these things. However, when we looked at those two rocks, the transformation was guided by certain variables. In most cases, or the most prominent variables, are pressure and temperature. That is, let us say the pressure and temperature existing at the surface of the earth when the sedimentary rock formed, and the pressure and temperature deep inside the earth where the metamorphic rock formed without significant change of chemistry. Now, we can show this transformation in a simple system. This simplest system will be where there is only one component is involved. That is, one minimum number of chemical entity which will define several phases. So, if we look at a geological example of a chemical system, one component chemical system, we can think in terms of a system which is defined by the component Al2SiO5. There are three phases or known phases of Al2SiO5 which occur in this form qualitatively in space which is defined and governed by pressure and temperature. Now, these three phases are known as kyanite, selenite, and andalusite. However, we could have taken any one component system like water, where the component is H2O and the phases will be vapor, ice, and liquid. Now, when we look at these three phases, possible phases of one component which is Al2SiO5 and we try to find a relationship which will define a well-defined relationship between phases and components. Then we can think of an area in the field of kyanite. Now this area in the field of kyanite is defined by boundaries of temperature, which I am naming as T1 and T2. The T1 is lower temperature as the temperature increases away from this origin, and T2 is higher temperature, and similarly P1 and P2 pressure, where P1 is lower pressure and P2 is higher pressure. Now if I change temperature from T1 to less than T2, from T1 to less than T2, at the same time I change the pressure from P1 to less than P2, there will be no change in the system. That is, we will always remain within this area. What it implies that within defined limits, we can change the two variables and the system will remain as it is. So if I try to express this in form of a mathematical equation, then I will try to define this shaded area as made up of one component where phase, as we see, is only one phase is present, so it is defined as one phase, but I have freedom to vary both the variables, which means that I have 2 degrees of freedom. So this expresses the relationship or the boundaries of this area. And for the sake of convenience, I will just write this in form like this, where I have related phases, degree of freedom and component. If I try to substitute it with the number, then for this area there is one phase, 2 degree of freedom and one component. To balance this equation, I need to write 2 here. So for as far as this area, shaded area is concerned, P plus F is equal to 2 plus C, that is phases plus degree of freedom is equal to 2 plus number of components. Now let us look at a relationship on this line. On this line, we have both phase kyanite and sillimanite coexisting. So for this line defined by cross, I have number of phases as 2. If I try to change temperature from T3 to, let us say, temperature T4, the system will revert to one phase. However, if I change temperature from T3 to T4 and dependent on that, I change pressure from P3 to P4, a temperature which is dependent on one independent variable, then the system will not change. That means that for coexistence of 2 phases, I have 1 degree of freedom. And of course, this remains as a one component system. Let us rewrite the situation at cross in form of a similar equation, that is P plus F is equal to C, and try to balance. We have 2 phases, 1 degree of freedom, 1 component. Again, as you see, to balance that we have to write 2. And if we compare the area, the shaded area equation and this equation, we see that they are quite similar. Let's look at the third option and third situation, which is here. Now this point marked by a small circle represents coexistence of all three phases together, that is kyanite, sillimanite and andalusite. So for this we have number of phases as 3. Of course it is one component system. Now if you see that there is no independence to change either of the variable, that is if I change temperature I will either be moving towards two-phase assemblage or towards single phase. If I reduce, I will move to andalusite field. If I increase pressure, I will be moving at the same temperature, I will be moving in kyanite field, which means that there is no degree of freedom to vary any of the variables, which means that F is equal to 0. Let us write this again in form of an equation like this, and you see we have 3 phases, 0 degree of freedom, 1 component, and as you can see that to balance still we require an equation which is exactly similar to the earlier 2 equations. So we see graphically that for this one component system, considering the variables, 2 variables which we have thought, the solution for every part of pressure, temperature, space is definable by one unique relationship, irrespective of wherever we are there in the PT space. Now this is an extremely useful relationship, and this is known as Gibbs phase rule. Gibbs phase rule allows us to know for a certain number of components how many phases are possible for different variable situation. For example, this is because in this area we can change both the variables, so this is known as divariant area. Whereas along this line we can change one variable independently, so this is known as univariant line. Similarly, at this point we can change neither of the variable without disturbing the system, so this is known as invariant point. Please pay attention, divariant area, univariant line and invariant point, that they are geometrically distinct entities. One is a point in a 2-dimensional space, the other is a line, and third is an area, and each have their distinct degree of freedom. If for geological situations, often we say that for a range of pressure and temperature, the conditions are valid. If we consider a range of pressure and temperature, which means 2 degrees of freedom, if we consider a validity of certain situation for a range of pressure and temperature, that is 2 degrees of freedom. So if we make F is equal to 2, then this equation reduces to P is equal to C, that is the number of phases equal to number of components. So if we can define a chemical system which is valid for a range of pressure and temperature, then the number of phases will be equal to number of components. And this relationship is called as Goldschmidt's mineralogical phase rule, which is again very useful, as we will see in subsequent discussions.